Hello, and welcome. We all know copper for its amazing ability to conduct electricity and heat. But pure copper has a weakness. It softens and loses strength when things get hot. This is a big problem for many modern technologies, from aerospace parts and electrical connectors to fusion reactors and high-speed trains. That's where high-performance copper alloys come in, engineered to handle extreme temperatures and stress while keeping as much of that vital conductivity as possible. So, how do we make copper tougher? Metallurgists use several clever techniques, often together. One is solid solution hardening, where other elements dissolve into copper, strengthening it, though this usually dips conductivity a bit. Then there's strain hardening, or cold working, like rolling or drawing copper, making it stronger and harder but less ductile. A really key method is precipitation hardening. Here, specific elements are added that form tiny, strong particles inside the copper after heat treatment, acting like roadblocks to stop the material from deforming, especially at high temperatures. Similar to this is dispersion strengthening, using stable particles like oxides, which are great for thermal stability and resisting creep. Finally, refining the grain size or even engineering the alloy at the nanoscale can bring extraordinary boosts in strength and heat resistance. The search for even better copper alloys is always on. A huge recent breakthrough is a copper-tantalum-lithium nanocrystalline alloy. By adding a tiny bit of lithium, it forms a unique nanostructure with copper-lithium precipitates shielded by tantalum. This alloy is incredibly stable, holding up at 800 degrees Celsius for over 10,000 hours with hardly any loss in strength. It's a game changer, offering performance similar to superalloys used in aerospace. Other important groups include copper-nickel-silicon alloys, great for electrical connectors and springs due to their strength and decent conductivity. Beryllium copper has been a champion for strength and fatigue resistance, but beryllium's toxicity is a concern, pushing research for safer options. Copper-chromium-zirconium alloys offer a fantastic balance of high electrical conductivity and mechanical strength, making them ideal for things like rocket engine combustion chambers. And let's not forget dispersion-strengthened coppers, like those with aluminum oxide, designed for the highest temperature strength while keeping good conductivity, perfect for welding electrodes. New alloys are also being developed for 5G tech, electric vehicles, and fusion devices, sometimes targeting tensile strengths over 1000 megapascals with good conductivity. Creating these advanced alloys isn't straightforward. It requires precise control over composition during alloying and casting. Then, specific combinations of heat treatments and mechanical work, like rolling or drawing, are crucial to get the desired internal structures. Powder metallurgy and even 3D printing, or additive manufacturing, are also being used, with NASA developing alloys like GR-COP for 3D printing rocket parts. Welding these materials also needs special attention, often requiring heat treatment after joining to restore properties. So, where do we see these super coppers in action? In aerospace and defense, they're in heat exchangers and rocket engine liners. In electric vehicles, they're vital for efficient heat management and electrical systems. For electronics, think miniaturized connectors and 5G components that need to perform reliably, sometimes at high temperatures. The energy sector uses them in nuclear fusion reactors and continuous casting molds for steel. And in high-speed rail, they're essential for contact wires that endure wear and heat. Looking ahead, the world of advanced copper alloys is buzzing. Researchers are exploring new alloy combinations, refining manufacturing for better results, and using powerful computer simulations to speed up design. A big focus is finding environmentally friendlier alternatives to elements like beryllium without losing performance. The continued push for stronger, more heat-resistant copper alloys is vital for future technological leaps, paving the way for more efficient and powerful systems across many industries. Thanks for tuning in.